NIM is a simple but potentially infuriating ancient two-player game. You have some counters or matchsticks and you're allowed to take a limited number in each turn, say 1, 2 or 3, and the winner is the person who takes the last counter. Sometimes it's played the other way round so that the player left with the last counter loses. This is called a misère game, but I think there's enough misère in the world as it is, frankly, so we'll play the happier version of the game today. Thinking about this game makes a great maths investigation, and it can be a good computing activity too. Challenge your students to write a program that will play and beat a human, or modify and improve the programs I'm going to show you in this video. As you can learn a simple trick to always win NIM, it makes a great game as well to annoy people with, as Matt Parker of Stand Up Math shows you in his superb video about the game, and he also has a 1960s American plastic computer version of it. Do watch his video just as soon as you finish watching this one. The wonderful folk at the Enrich project at the University of Cambridge have also written up a lovely simple version of the game here. I used to use the Enrich games and resources a lot when I was teaching primary school maths, and I highly recommend them for creative maths investigations. Back in the 1970s, there was even a version of NIM for the Sinclair Cambridge Programmable Calculator, and you can read a bit about that elsewhere on my blog. Anyway, I decided to see if I could write a BBC microbit program so that the microbit could play a human at NIM and always win. Perhaps you could challenge your students to do the same and see what they come up with. Can they identify winning strategies for the game and then abstract them into a working computer program? I approached this challenge by taking the really simple version of the game that Enrich have and applying Matt Parker's strategy from his Dr. NIM video. The key here is to think of the end game, the position you want to get your opponent into. In the Dr. NIM game that Matt Parker shows in his video, you have 12 marbles and you can take 1, 2 or 3 at each turn. So what he does is to chunk the games into multiples of 4. In every go, whatever you take, Dr. NIM will take whatever number he needs to make sure that you've taken 4 between you in the 2 turns. So if you take 1, Dr. NIM will take 3. If you take 2, he'll take 2. If you take 3, he'll take 1. Now, we're computer scientists, so we always want to abstract some kind of pattern if we can to make coding more efficient. So straight away I noticed that if the human takes n counters, Dr. NIM takes 4 minus n counters. This is the sort of thing that could be useful when we come to write a computer program. I also noticed that with the option to take up to x counters, you want to break it down into chunks of x plus 1, so that if your opponent goes first, you've always got the advantage. You want to make sure that they always have x plus 1 counters at some point when it's their turn to go. So in the Dr. NIM game, where you can take up to 3 marbles in each go, you want to make sure that at some point there are 4 remaining. Hold that thought, we'll come back to it later. So back to our microbit version of the game. I'm going to follow the Enrich version of it and say that you can only take 1 or 2 counters in each turn, but I'm going to start with 9 counters instead of 7. This simple version is easier to think about, it's easier to work out all the permutations, and it's going to be easier to code. Also, we can use microbit button A to take 1 counter and button B to take 2 counters, so we've got a nice simple user interface. So I coded a version for the microbit. Let's play it and try and beat it. Okay, so let's try and beat the microbit at NIM. So we start off with 9 counters. If I press button A, it means I'll take 1 counter. If I press button B, it'll take 2. So I'm going to start off by taking 2 counters. So it goes down to 7. The microbit has a little think, and then it takes its turn. And it says, I take, let's see what it decides to do. I take 1. So it's taken 1 counter, we're now left with 6. So remember, I can now take 1 or 2. I'm going to take 1 counter this time. So we go down to 5 counters remaining. Microbit has a think, and then it says, I take, how many is it going to take? I take 2. So what are we left with? Right, we're left with 3. I think the microbit may have me in a bit of a corner now. Remember, I can only take 1 or 2, and the winner of the game is the player to take the last counter. So I am a bit stuck here. So I'm going to take 2 counters, which leaves 1 counter remaining. I wonder how many the microbit's going to take. Let's see. I take 1. And the number of counters goes down to 0, and the microbit has won. It says, I win! Exclamation mark, and the program sits there for a bit, and after a while it will reset itself and it will go back to 9 counters. Now, we could play many more games, but trust me, the microbit will always win. So how does it work? Remember Matt Parker with his 12 marbles, which he treated as 3 lots of 4? Well, he had sets of 4 because the choices were to take 1, 2 or 3. The chunk you're working with should be 1 more than the highest number you can take in a turn. We can only take 1 or 2 counters in our microbit version of the game, so we'll treat it as 3 lots of 3. We'll make the human go first. Remember, in a pair of turns we need to make sure the human and machine have taken 3 counters between them. Each time, if the human takes 1 counter, our program will take 2. If they take 2 counters, the program will take 1. As there are only 2 choices at each turn, we can hard code this into blocks that follow each button press: A for 1 counter, B for 2. Here we use a function to update the display and check if the game's over. I added a bit of logic to show different messages depending on whose turn it was when the last counter was taken, though with these numbers the "you win" message will never be displayed. Try altering the number of counters you start with and see if that makes a difference. Does the program still work? Now, do you notice anything about these 2 sets of code for button A and button B? That's right, they're very similar. There's a pattern here, and when computer scientists spot patterns, they get very excited because there's an opportunity to be clever and make the code more compact and efficient. We do that in this new version of the project by creating a function that does the same work, just slightly differently depending on how many counters the human took. Remember that formula 4 minus n earlier? No? Well, no matter. I spotted that in Dr. NIM, if the human takes n marbles, Dr. NIM would always take 4 minus n marbles and be guaranteed to win, because that game works in blocks of 4 counters. And I kind of use that here. The variable human go keeps track of how many counters the human player took. We set the number for the computer to take by using 3 minus n, or 3 minus the human go. Our game works in blocks of 3, so we set the computer's go to be 3, or minus 3 here, minus the human go. So why is it minus 3 here and not 3? I'm using negative numbers here just to make the block simpler when we change the total number of counters stored in the counters variable. MakeCode doesn't have a block to change the sign of a number. Well, not yet. I'll have to see what I can do about that. I've managed to sneak at least 1 new block into MakeCode, possibly even one used in this project, and it would be fun to have another one to call my own. So this version of the code works in exactly the same way as the previous one. It's just a bit more efficiently coded. It's cleverer using a function to avoid repeating 2 very similar sets of code. But is it easier to read, follow and understand? Probably not. This is something that would make a great discussion point with a class of students. Which version of these programs is better? Which is easier for someone to come along and understand and modify, or if even you yourself look back at your own code months or years later and wonder how on earth you wrote it and what it does. The first one makes it very easy to follow what happens in each case. But if you want to adapt this to play a more complex version of NIM, say with 12 counters and the ability to take 1, 2 or 3 at each turn, the version with the clever function is probably going to be more adaptable. Have a play with these projects, and if you adapt them to make more advanced games of NIM, let me know. You could use shake gestures, wire up 3 tinfoil buttons to the pins, or use the touch logo on the new microbit V2 to get more button inputs for more choices. Like the Dr. NIM game in Matt Parker's video, perhaps you can also create an equalizer mode where the poor human player has at least a chance of winning. Have fun annoying your friends and relations with your unbeatable NIM microbit machines.